So, hello friends. Thank you for coming. Today, Darren here from Celestial. He works with space lasers. It's really freaking cool. Like orbit-to-orbit laser communication. I always tell people he's the space laser guy. It's great. But he's going to tell us about writing a Lisp interpreter today. So thank you all for coming. And as usual, we'll get food afterwards. And with that, thank you, Darren.
Is the go live button hit?
Yeah.
Cool. All right. Let's start. Okay, so good evening, everyone. My name is Darren, and this evening I'm doing this because my mic sucked, I think. So I'll be conducting today's workshop, writing a Lisp interpreter. And just a disclaimer, I don't write Lisp professionally. I don't write compilers or interpreters professionally. This is just a hobby. I just happen to be a bit bored and found some time. So I'm not an expert on these things. I learned a bit at school, but that's pretty much what I know. Okay, so the agenda for today, I guess is going to take around 2 hours, a bit short, a bit theory. So we'll start with theory, introduction to compilers, and then two hands-ons, writing a Lisp interpreter. It's more like copy-paste, but yeah, you'll be typing something. And the next one will be using the interpreter itself to write programs in Lisp, which is this weird language if you haven't seen it before, and hopefully learn some concepts in functional programming along the way. So ideally, you should have a laptop with your favorite IDE editor. I don't judge, but at least you should have Python 3. You can use Python 2, but no guarantees. Okay. So I'll start by explaining the two keywords in the title, which is Lisp interpreter, and I'll start with defining the word interpreter. But even before that, let's start with the word compiler, which if you do development, you may have seen from time to time. So what a compiler kind of does is that it converts source code into machine code, right? Which is basically something the computer can understand. And the machine code is usually what we call assembly language. So I'll just give you demonstration of how disgusting it looks like. I hope you will never have to deal with it. So I'm just disassembling some random binary on my machine, and this is a preview of what it is. So this is what the computer really understands. This is what the CPU, these are all the instructions that your CPU actually runs. I don't understand any of it. So that's why we need compilers. So sometimes compilers, yes, please.
Sorry, gotta interrupt for a second.
Sure.
You're having trouble with.
Oh, do it.
Yeah. Can we go to settings here? And can we go to output?
Output.
And select software here.
I have a GPU.
Select software here.
I have a GPU. I don't have a GPU.
You don't have a GPU.
I don't have a GPU.
You don't have a GPU.
Yeah.
That should be fine. Yeah, select very fast.
Very fast.
Maybe do super fast.
Super fast.
Yeah, what's happening is it's not.
Is it lagging?
Yeah.
Resolution.
So choose video encoder here. Maybe we can use a better encoder. Nope. Okay. Try changing the video bitrate down to 2000 kbps.
Okay. Cool.
Alright, and let's hit apply.
Okay.
And hit OK.
Okay.
And that's it.
All right.
Thank you.
Sorry, AV audio-visual problems. Sometimes compilers convert machine code into an intermediate language. So, so this is, for example, Java. When you use Java, the compiler converts the Java code into Java bytecode, which runs on Java virtual machines. And this stems from an idea from 1995. The Java guys, they were like, okay, I'm going to write once and run everywhere. So the idea is you compile a Java code once into this bytecode, and then you can use your Java app on, I don't know, your phone, your Mac, your Intel PC, and it'll all work because there's this additional abstraction called the Java virtual machine. But that's not irrelevant. If you're curious, you can look that up. Sometimes compilers convert your source code into another language. For example, if any web developers here, if you use TypeScript, which I applaud you for, the TypeScript compiler compiles TypeScript down into JavaScript because your web browser actually doesn't understand TypeScript, but it does understand JavaScript. And if you don't use TypeScript, but if you use, say, React, right? If you use JSX with those fancy tags, right? So those are just syntax sugar, which the React compiler kind of converts it into pure JavaScript anyway. So just an example of compiler things happening even though you don't realize it. There are other things, other weird languages like Elm, which is a functional language for front end. It also converts to JavaScript. And the process of converting source code into another language is for the more pedantic people, they call it transpilation, but I don't really care. I mean, it's not that important. Okay, so we've kind of gone through compilers, and an interpreter is like a compiler, but it reads, in general, it reads and executes source code line by line, and it doesn't really output any, produce any output file. You know, it's like you use some compiler and you say compile, it will just generate this executable binary, but interpreters don't. So some examples would be the Python interpreter. If you guys are Python developers, if I do this, Python 3. So this here is the Python interpreter. And I know I'm one of the weird guys light mode in the IDs. So you can do stuff like this, A plus B, 3, I don't know, print, hello world. Yeah, so this is an interpreter running. You give an input, it immediately evaluates what you're doing. It outputs to the console, and there's no like file being produced anywhere. Okay. Another example would be your web browser console. For the web developers out there, you press F12, DevTools, you click console, you can type JavaScript stuff to query your page. So that's also interpreter for JavaScript. And the last example is what you will be building or copy-pasting in a few minutes. All right, so why should you care, right? Yes, Beach.
Sorry. Sound trouble here.
Sound trouble, jeez.
Yeah.
Okay.
So the video keeps like skipping. So we're actually missing what you're saying.
Okay.
So let's hit settings again.
Yep.
Let's go to output.
Output.
And let's screw it down to 1,000.
1,000, okay.
And let's change the.
I mean, they have the slides
Yeah,
anyway.
let's change it to the encoder preset. Ultra fast.
Ultra fast. Okay.
And
Doesn't it look like the.
let's try that.
All right.
Thanks.
All right.
Sorry, guys.
Shitty quality. Let's go. Okay. So, and of course, the question on people's minds here is like, okay, why should I care, right? Why am I here? Why am I here today? Why should I know about writing compilers and stuff? So the thing is, to most people, right, compilers are magic. It's this black box thing. You download from the internet. You type source code. It generates the file. Done, right? But someone had to sit down and write the compiler, right? You'll probably never have to write a compiler ever professionally. I know I don't. I just use them. But it's still useful to know how they work. And some interesting parts of the world of compilers are like how parsing works, which I'll explain later. Performance stuff, so different compilers have they do things to your code to improve the performance. And sometimes it's good to know what happens under the hood if you encounter strange things in weird languages. For example, like if you guys do Java and you play around with generics, then you should know that you can't access the type information at runtime because the compiler does type erasure and yada yada yada. So if you are into those things, then yes, you need to know that the compiler does those under the hood. But in general, yeah, so those are the useful stuff. And you also see through this workshop, right, how people invent programming languages. Like they don't just sit down, think of something, and make this magic thing, right? You see how they actually make this thing, how they implement a programming language. So in this workshop, thanks to Peter Novick, this AI scientist, he has a few blog posts where he used Python to write a Lisp interpreter. So what we're doing here is just a slightly modified version of it. And I just want to emphasize that we will be implementing a programming language, which is Lisp, in another programming language, which is Python. So if that is not mind-blowing to some extent, yeah, I hope by the end of the the workshop, you'll be a bit mind blown, right? It's mind blowing to me. So why am I doing this? So for me, it originally started as a side project for me to learn compilers and, God forbid, C++ because I had to learn it for work. So I thought, okay, I'm gonna kill two birds with one stone, gonna write a compiler, I'm gonna learn how to write compilers and learn this beast called C++. So I used the original Peter Novick reference. I started to re-implement it in C++. And yeah, I made some progress. So, but I thought for this workshop, I'll just use the Python one instead because I don't want to torture you guys with the C++. All right. Any questions about interpreters before I define the word Lisp? Okay. So, the next word I'm going to introduce is Lisp. So, what is Lisp? Lisp is a vintage programming language invented very long ago, but it's still used today. Various dialects of the language, as they call it. Clojure, which actually compiles down to Java bytecode. Common Lisp, Scheme, which is more like an educational teaching programming language. But they all kind of look the same, which is like, you see those parentheses at the bottom? Yeah, they all look like that. So it's a functional programming language. I don't know about you guys, but when I first saw the word functional programming language, I thought it was functional in the sense of not dysfunctional. But yeah, then I learned that it was just about functions and functions and functions, which you'll find out later. It's really all about functions. So as you can see, if you haven't seen Lisp before, you'll find it very weird. And it's simple for the machine to read, but it's difficult for humans to see. And you will see and you will understand when we go into a bunch of Lisp programs that we will be writing later. So what's happening here is, okay, we begin a program, we assign 10, the value 10 to the variable r, and we do pi multiplied by r multiplied by r, right? It's a strange syntax with the operator in front. Usually it's like pi star r star r, but in this case it's like, you understand, okay. So once again, why should you care? Why are we here looking at Lisp, parentheses, and weird ways of writing pi r squared? So functional programming, I believe, will change. If you haven't done it before, it would change how you program and think. For example, there are no for and while loops, which is a surprise to most people the first time they get in contact with it. But we can do useful things, as you will see. And the concepts and patterns are useful if you still use imperative languages every day. I do, right? I use Golang and C++ at work, but I do apply some concepts and patterns. And languages these days, they have like libraries and functions that are kind of close to, that would derive from functional languages, like map, filter, right? Yes? Yeah, sure. The definition of imperative is like command. Okay, do this, do that, right? So it's like in, let's say, Python or JavaScript, you're literally writing instructions in serial, like, okay, A equals to B. Okay, A equals to 1, B equals to 2, now add A plus B, then print hello world, that kind of stuff. Yeah. A functional language is not imperative, as you will see. Okay, I mean, it's arguable that it is imperative because you're still telling the computer to do something, but it's not as imperative as, let's say, Python or someone. Yeah, it's a spectrum. There's no like clean cut between in the spectrum of languages. So there are other functional programming languages if you want to enter the world of functional programming. Besides Lisp, there's Haskell, Standard ML, OCaml, Elixir, Elm. So yeah, if you are really interested, you can spend a lot of time on these things. So but more in the second half of the workshop. The first half we'll be writing our interpreter. So it's like we're in the land of Python, right? And then we'll move to the land of Lisp. Okay. Right. So I've defined those two words, and now I'll just talk briefly about compilers. There are compiler textbooks, lecture series, right? I'm just going to cover it in like 3 slides, so it's not anything comprehensive. But in general, right, Like I said, compilers, they take a source file, and source file, let's say hello.c, I'm assuming the C language here, and it spits out a binary, I'm assuming Windows here, hello.exe. And usually you just have this magic black box that spits out that, right? But inside a black box, in general, there are at least 3 stages, right? The first stage is lexing. So it converts, I'll give you an example later, don't worry. It converts the source code into tokens. If you do like ML and stuff, you would understand, right? You know, LLM, you take the thing, convert the tokens, blah, blah, blah. Okay? But it's not the same thing, which I'll explain later. And the next stage is parsing. It takes the tokens, and then it converts the tokens into something that the computer can understand, right? And it converts to something which is called the abstract syntax tree. It's a abstract word, and I'll explain what it is later, right? And it's not that difficult. I'll skip the stuff in the middle. I'll just go straight to the last stage, which is code generation, which basically takes the abstract syntax tree or whatever is in the middle and churn out that assembly code that we saw just now, right? Then it just churns out these things, kind of. So most modern compilers these days, in the middle, they do things like type checking, making sure that you don't add a float to an int or something like that. They do some analysis, they do some optimization. So for example, if you have a block of code that's useless, it does nothing, right? It does nothing to the end. It would just think, okay, this is going to waste CPU cycles. It would just remove it, right? And it makes no difference to your program in the end. So I'm going to skip those stages. They're not relevant for today, but just letting you know that modern compilers do those. Okay. Interpreters are slightly different. So you can see that the difference between the 2 slides is that instead of code generation in the last stage, it's evaluation, right? Because we want to quickly evaluate the thing, and then we want to spit it out in the console. So I'm going to start with the Lisp example. So as you have seen earlier, the operator is in front. This is basically computing 1 plus 1. Okay, the operator is in the middle, the first operand and the second operand. So this is how you write 1 plus 1 in Lisp. The parentheses are necessary. Yeah, that's how it is. And then we do tokenization. We split the tokens into, we split a string into tokens. So we have a left parentheses, we have the operator, we have the number 1, 1, and a close parentheses. And then the parsing will give you an abstract syntax tree, which you see here. Doesn't look anything like a tree, looks abstract, right? I'm sure you're confused, how is this meaningful? But it basically converts to something that the computer can understand, and this happens to be something that the computer can understand, and I'll show you an example later, right? So basically, it converts this, and it says, okay, the parentheses is not necessary, I'm gonna convert it to this thing, this internal representation of the program, and then the evaluation kind of works like this, right? It sees the plus, and it's like, okay, I need to add something. What is the first thing I need to add? Then it goes on to the next element in the list. It's like, oh, I need to add 1, and what's the next thing? 1. Then it just does 1 plus 1, and it gives 2. In a nutshell, this is how interpreters work, kind of. All right. Yeah, so the interpreter that we are going to write today skips the middle part. It's literally 3 stages, right? And each stage itself is quite heavy on their own. Okay. So previously you saw this thing that looked nothing like a tree. I'm going to show you something that looks like more like a tree. But to the uninitiated in computer science, a tree is a normal tree pointing downwards. So usually your tree goes up, right? But computer scientists like trees the other way around. Just think of it that way. So let's say we're not happy with just evaluating 1 plus 1. We want to do something a bit more complicated. So we have this expression. So this is what humans would see, right? This is what you do in school. Basic arithmetic and so on. But after some processing, internally, the computer sees this. right? So this is a tree, and it's kind of abstract, and it is a it is a representation of the original syntax. Okay, I'm trying my best to explain to map it to the term. So it converts to this, and you'll be wondering, okay, what can I do with this? All right. So basically, to the computer, this is actually very easy to operate on. Basically, it means add 2. Okay, try to follow, right? Give me the sum of 2 and the product of 3 and the difference of 4 and 5. Yeah. So you can see it's a very structured way of doing things, which is what computers like, right? They like structured way of doing things. You give it this, they like, yeah, computers won't know what to do with it, kind of, right? So we're going to evaluate this expression. I'm going to show you step by step how a computer would do it to a first approximation. So first, it would evaluate the bottommost expression, right? The difference between 4 and 5, which is -1. Then we replace this whole subtree with -1, and then going bottom up again, we'll take the product of 3 and -1, so that's -3, and finally, there's nothing left but to add 2 and -3, which is -1. So there we go. So this is how a computer, in a very structured way, evaluates expression, evaluates an abstract syntax tree, right? But compilers don't just do arithmetic; it does other things. So we'll see later on in the example code what else it can do. Okay. So, any questions so far before we move on to the hands-on? Okay. If not, then in case you have not done it already, please check out this Git repository, and we'll be mainly working on the file x.py, stands for exercise. The answer sheet is in main.py if you want to just jump straight into the actual implementation. So there's some bugs and gaps in x.py, so which is what we'll do to fix during the workshop. Okay, so if you don't use Git, that's all right. Oops. Just go to GitHub, just click on the link, click on code, just click download zip, unpack it wherever you want, and then you can run the code. Yeah. So I'll just give everyone some time to set it up. Okay. Is anyone still setting up? It's fine. It's okay. Yes? 3. Doesn't matter. Yeah, shouldn't matter. Yeah. All right. So. While you're doing that, oh, what happened? I should be moving this to the right. Okay, is anyone still setting up? No? Okay, so I'll just proceed. So so before we start with the exercise, I'll just show you what we'll be building, the final outcome, and then hopefully that gets you excited. So we can run the main file with just this command. You can try it now if you want. So we can do what we did just now. 1 + 1 gives you 2, right? We can do something a bit more sophisticated. I know the answers are there, but I'll just copy paste the stuff so that okay. Yes.
Space is necessary when typing in this command.
Yes. 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 You'll find out why in 10 minutes. Yeah.
Well,
Mm, right. So, for example, in this, in the next example, we're saying, so in a classical language, this is equivalent to saying A equals to 2, B equals to 3, A times B, right? Whereas this is the Lisp way of doing it. We can do things like create lists, which is another way of saying arrays. Of course, if you use Python, then maybe list is Lisp may be a familiar thing. So Lisp is a contraction of list processing. That's the historical term, and you kind of find out why later on, because we will be dealing with lists a lot. Yeah. So here I define my list, and I can print it out. 3 elements, 1, 2, and 3. I can take the head of the list, which is the first element. I can take the tail of the list, which is the thing cut off, like like a snake with the head cut off, right? That's basically the tail. Yeah, kind of. And so that's the last 2 elements. We can run a few things. So if you type load examples, it will load a file called examples.lisp, which is, as you can see, we are entering the world of Lisp here, a bunch of parentheses and stuff, which we will look at later. So load examples, we can get the length of the list, which I know you must be wondering, this is simple, right? Yeah, so it says the length of this list is 3. We can do some math, factorial, and so on, okay? So there are things we can do, and I'll go through the rest later on. So hopefully this gives you, this got you a bit excited about what we'll be building. So now I will go through the example.py file, and let's do some copy pasting kind of. Okay. Anyone has any questions so far? Anyone managed to run those examples? Yeah, 1 plus 1, all good? Okay. So, yes.
So can you cannot find variable len? Cannot.
You need to load examples. Yeah, yeah.
If anyone has trouble, you can wait me down for that.
Yeah. Yes.
So by accident, I didn't. So I tried to type KOXS.
Yes.
But by accident, I didn't include the parameters.
Uh-huh.
And that is because of the output.
Yeah, so let's try that. Hit access. It just gives you, so this thing is not perfect. Yes, bugs, right? So in a more in a better compiler, then we should have better error handling. In this case, I didn't want to do that. Yeah.
My question is, what is it called exactly? Is it like the memory load?
So we'll find out later, right? Because when writing this, we're actually going into the internals, and you'll see what these things actually mean. Yeah. Okay. So let's start with some definitions. Let's ignore for now. The thing on the left is what. Okay, so the way to read this is a Lisp string is a Python string. Yeah, sounds obvious. A Lisp number is either a Python integer or a float. Lisp atom, this is a concept in Lisp, is either a string, a number, or a symbol, which I define here as a class, which is a subclass of string, and let's just not care about this for now. I'll explain why later. And Lisp list is a Python list, very convenient. That's why we use Python. A lot of things are kind of built in. Imagine doing this in some other language. And a Lisp expression is either an atom or a list. Yeah. Okay. So, and I define this weird thing called quote because we are dealing with strings. That's fine. Okay. We don't have to do that later. So, if you recall from the slides, right, there are 3 stages: lexing, parsing, and evaluation. The other word for lexing is token, but here, yeah, I just call it lex. Okay, so sorry, even before going through this, I'll just go to the main function. By the way, you can see that we wrote all this in less than 200 lines, with the help of a lot of Python libraries, of course. Yeah, but still. Okay, so this is the main function, right? If name equals to main, run this thing called REPL. So this REPL function here. So REPL, what people call the REPL, stands for read, evaluate, print, and loop, right? Just like how an interpreter does. It reads the input, it evaluates the expression, right? Calculates 1 plus 1 equals to 2, prints out 2, and loops again. So it just keeps going on and on. This is how an interpreter works. So, by the way, if you compare this to the original Peter Novick implementation, you can see some similarities. So this whole chunk over here is just fancy. It's just for me to be able to load examples and load those files, so you don't have to care about them. The most important part is this, right? This is basically the REPL itself. Okay, so we have a string. We read it, we lex it, we convert it into tokens, we parse it. Yeah, if you recall from the slides, lex, parse, evaluate is the same. Lex, parse, evaluate, return the value, and this is just like random error handling, and then print. So the lex, parse, evaluate is basically, okay, lex is the read, okay, that's the read, which is the Python input function, and then the eval in the REPL is basically lex and parse and eval, then finally print. And then there's a infinite loop, right? So that's pretty much it. Okay, that's how the interpreter works overall. That is what is happening when you type stuff, right? I type stuff here, 1, 2, whatever. It does all this. So
Yeah.
it is, yeah.
Or it's a problem with his computer communicating on the network.
I don't know. Usually I'll just like this.
That usually does it?
Yeah, that usually does it. Yeah. Sure. Oh, okay. It's back up, but is it gonna last?
I use my lasers.
Okay, maybe can you leave that in the background just to maybe
Sure.
try to keep the connection alive? Granted, the stream should be doing that.
Sure. Okay.
All right, let's go back to the stream.
Okay, stream is back up.
All right.
Okay.
Cool.
Cool.
That was
sorry, guys.
weird. We're back.
We're back. Okay. Okay. Where was I? Lexing. Yes. So the one-liner lex function. Okay. We'll move on to parse. Right. So if you recall, after the lexing, we do the parsing, and we would really want to just move this away to parse the tokens that we just created. So, am I on the right page? Yep. So now, I was thinking about it, and I thought, okay, I'll go through an example. Yeah, it's a bit hard to understand, but I think working through an example will be useful. And I think the best example here would be to try to parse something like a more complicated expression. So let's say, I don't know, this, right? So if you, I hope you've gotten used to Lisp. So this is 1 plus 2 times 3. That's 7, right? Yeah. Okay. So after we tokenize, we should get something like this, right? It's just adding spaces to stuff, right? Nothing fancy, just this. So what we want to do now is to convert this thing into the abstract syntax tree, that tree thing that doesn't look like a tree, right? Something like this, kind of. Okay, so I'm going to step through the parse function line by line, and I hope you guys can follow. So let's see. First of all, it checks if the token list is empty. If it's not empty, then it will throw a fit, but in this case, it's good. So this is what happens if you pass empty thing. It will just say unexpected EOF, right? Whatever. The first thing it will do is that it will get the first token using the function pop. So what does pop do? Pop returns, removes and returns the function at index 0. Okay, at the index. So in this case it's 0. So we get the first token. So what is the first token? Maybe let me just do this after lexing. Right, we get this. So token is the first thing. So that's, in fact, I'll do this. Okay, so this is I know this doesn't look like a list. I'm just lazy to type the commas. So I just hope you can follow and do a mental split using the white space. Yeah. So token is the first element, so we pop it. And what pop does is that it actually mutates the list here, so we can pop it off, the tokens list. So we get this. This is the current state. Now we know the current token is open parentheses. So it says, okay, is it a open parentheses? Yes. Let's create this thing called L, right? I wanted to change the variable name, but this was the variable name that was used in the original Peter Novick implementation, so I didn't want to change it that much in the end. So L is an empty list, yeah? Now, then it goes into this while loop, and it says, okay, while the first element is not closing parentheses, and I know this looks weird, but hopefully you understand at the end, do this, right? So let's see, is the first element of tokens closing parentheses? No, so it isn't. So we append to L parse tokens, right? Which is this. And at this point, you might notice something a bit unusual, in the sense that parse is a recursive function, and what it means is that parse is calling itself, right? So under some conditions, it'll call itself, and that may take a while to get used to, but yeah, just try to follow the explanation. So parse tokens. So what is tokens? Tokens is this, right? So now we enter another instance of parse where tokens is, I should just copy this, is this guy, right? And then let's pretend that we are running parse again, right? Now tokens is, so then in this case token is the first element, which is a plus, right? And then now the question is, oh, it's is token open parentheses? Nope, it isn't, right? Is it a closing parentheses? Nope, it isn't. What else is it? So we fall into the else clause, and it says, okay, return an atom. Okay, pass the token into this function called atom, and return it. So let's see what it is. So an atom, right, is a function that takes a string and converts it into the atom, right? A Lisp atom. And the comment here originally by Peter Novick is very helpful here. Numbers become numbers. Every other token is a symbol or string. Let's see how this works. So this is where Python kind of shines when it when it comes to writing interpreters, because we can abuse a few things here by using exceptions, which is not recommended usually, but this works. So we first try to say, okay, is this thing an integer, right? So we know our token was a plus, right? Can this thing be converted to integer? Nope. So we throw an exception, but we don't do anything funny. We try again. Can this thing be casted as a float? Nope. Looks nothing like a float. And then we try again. Does this thing look like a string, right? Meaning, does it start with a quote and end with a quote? If yes, we remove the quotes and return it, the string. We'll touch on strings later. If not, we create a symbol, right? And if you recall, a symbol at the beginning is a class that takes a string. It's just a subclass of string. There are no other fancy methods inside. Yeah. Okay. So that was our atom function, and let's go back to parse, and I know we are still in the second run of parse. So in here it says, okay, return a symbol of plus, right? So, and then it says, and then if you go back to this function, because the second call has ended, and it returned this guy. So here it says, okay, I'm going to append to L a symbol plus, right? Then here we say, okay, symbol plus. Okay, so cool. Our list now has one thing, and we have a lot more to go. Okay, so now we can take a shortcut by seeing, okay, we're not going to hit for the remaining symbols. Okay, the next symbol is 1. So let me just cut it here. The next symbol is 1. So if you use the same method as before, yeah, it's, this is going to be a number 1. Yeah, okay. I don't want to go through that whole thing again. And then we remove it. Okay. And then the next, this is where it gets a bit more interesting. We have now seen, okay, now we're encountering an open parentheses again, which means we enter this clause, okay, and it says, okay, create yet another L. Okay, by the way, if at the end of this you don't understand anything, that is fine. This is complicated. Yeah. Okay, it's fine, but it works. And if you don't understand, just at home, just step through the steps, right? And it should make sense. So it gets interesting because now we hit a new, another left parentheses. So we create a new L. So let's call this L2, right? So that we don't get confused with the L above, right? And then it says, okay, I open the parentheses, and using the same approach that we did just now, we're gonna go through this while loop. So I'm gonna pop this off. Yeah, and we're gonna pass the star, the 2, the 3, which, no surprises, it's symbol, star, number 2, and number 3. Yeah, otherwise I'll just be repeating myself for 3 times. And the next interesting part is, at some point it's gonna hit this, right? Because I finished a star, I finished a 2, I finished a 3, and now I have 2 closing parentheses left. So in this L2 world, right, it's gonna hit this, the while loop is gonna hit this condition, and it says, oh, finally I'm seeing a closing parentheses, so I should stop the while loop, right? I stop the while loop, and then I pop off the closing parentheses because that's what I saw, and I return the list. So if you go back home and you sit down and you do the linking and everything, you end up with something like this. Okay, and of course here we pop off this thing and we finish. So I know I've kind of skipped a few details, but yeah, time is of the essence here. So this is our abstract syntax tree, right? It starts with it's basically the sum of 1 and the product of 2 and 3. And of course you may be thinking, well, how is this a tree? Okay, I'm gonna illustrate, right? This basically represents, okay, I'm gonna use my ASCII art skills, right? You guys can understand ASCII art, right? So it's basically this, right? So this guy, yeah, if you stare at this hard enough, you'll see that they're kind of the same thing. Okay, it's just so this is just a tree represented in the list form. And at the end of the day, if we simplify this, all right, I'm just abusing syntax here, I know. We get this, right? And then if you stare at it hard enough, you realize that, hey, it looks pretty much the same as the original thing that we fed in, right? So So why are we suffering and going through all these things to get the thing that we wanted? Well, the thing is, this is a string, and this is not a string. This is the internal representation of the string in the program memory. Right? It is a list that has 3 elements. The first element is plus, second element is 1, and the third element is a list with all these things. Right? It gets complicated when you have, I don't know, like nested stuff, right? But yeah, there's a reason why I chose this example. So that's pass. Oops. And you can trust it to do what it says. It will pass the stuff. Okay. It's not excellent at error handling in some cases, but we're not building the perfect thing here, right? This is just an exercise. So, any questions so far? Yes.
It's a nice example. I just wonder, like in Python, is the technique of internal combining to the syntax tree
Mhm.
similar, or
Similar in other languages,
no,
or?
like the one which you're doing in Lisp?
Mhm.
Is it like works similarly in the Python
Yes.
compiler?
Yes. So Python. So what he's asking is that is the concept of parsing, which is to convert tokens into abstract syntax tree, the same in other languages such as Python, right? So in Python, maybe they don't use lists, right? They'll use advanced data structures like binary trees or some weird thing, right? If you do computer science, you have like more efficient data structures and stuff. But in Lisp, to be fair, in our interpreter, I could have used a binary tree to represent this, but that would just complicate things, right? It's nicer to use a list, and lo and behold, it looks exactly the same, like almost the same as our original thing. So there are pros in doing that. Yeah.
And then the second question is like, is there any reason why in Lisp they put an iterator to the front?
Mm-hmm. Okay, so the question is, in Lisp, is there, like, why did they put the operator in front? I think it's because it's easy to parse, right? It's easy. It's easy to evaluate. Yeah. Yes.
So
Trivia.
when you write, if you were to write an add function
Like function.
in Python, how would you write it? Not like the plus operator. If you were to define a function named add, what would the definition look like?
Yeah, it's going to be called.
It'd be like def add, right?
Yeah.
Now, what if you were to call that function? Right? No, call, right. So, yeah. And now if you were to call that function, it would look like this, right?
Yeah.
So Lisp and most functional languages. Now, the fact that we do operator, and then, I'm sorry, the fact that we do parameter like 1, and then operator like times, and then parameter 2, that's weird, right? That's not how functions normally operate. Normally it's function name, then parameter, then parameter, then parameter, so on and so forth. So functional languages are usually just more consistent, where it's like function name first, then parameters.
Yep.
So Lisp is just like, screw this exception for arithmetic. We're going to treat addition like any other function.
Yeah. Weird humans, right? Yeah. Weird humans.
Does that make
So.
sense?
Yeah.
Yeah.
Thank you.
So, yeah. I mean, the reason why we do parsing, okay, in a way, you could say, okay, if you want to write a program, right, I can just sit down and just write this assembly, right, and it will still work, right? But this is just too difficult. This is why people wrote compilers, so that they can write things in a slightly human-friendly language. Some people may think otherwise, but something that is a lot better than assembly, and do the translation, right? So that's the motivation. And of course, I guess people loved, I mean, I don't know about the history, but it turns out that arithmetic just happened to be like 1 + 1. So I guess people are like, okay, we're not giving this up. We have to find a way to pass this into what the machine understands, right? So that's history, I guess. Yeah, okay. So we've gone through lex and parse and atom. So if you go back to the top, we've seen, okay, lex and parse, we've done it. So now we have an abstract syntax tree, right? And what we are left with is the evaluation, which we have seen in the previous slide. The ping is still working, that's good. It takes the tree and it like squashes it down, right? Kind of, right? It takes this huge thing and squashes it and returns you one value, right? I think that's a nice way to put it. So let's go through eval. Okay, so eval is one of the most important. I think it is pretty much the core of the language. Everything else is just like prep work, right? To take this weird thing written by humans, convert it into something that the machine can understand, and now it's time to squash the thing into value, right? So, okay, let's see. So eval is a function that takes one argument. Okay, it takes two arguments. One is so x is the expression. So its type, it will be the abstract syntax tree. So let me just, I hope I did not delete that line. Yeah, let's do this. So just an example, right? So that you have some contexts. X, yeah. Yeah, once again, abusing syntax here, but I hope you understand. So we're trying to evaluate this abstract syntax tree. By the way, these are abstract syntax trees. Okay. Okay. So what it does is, so eval's job is to take these things and return you a value. That's pretty much it. And it does so with the help of an environment, right? Which here there is this thing called global environment, and the idea of an environment is that when you want to do an evaluation, you want to have like a context, right? So, and okay, that didn't make sense. Let me show you what an environment is. So, an environment is this thing. I will show you later. Yeah, but it's kind of like a dictionary, a map, some context, something that you can call upon at any time. And what it is you have this environment. And when you do the evaluation, let's say you see the word plus, right? Plus doesn't mean anything. So you ask the environment, hey environment, what is plus? And it says, oh, it is the Python function add. So you take the Python function add and you do stuff with it, right? If you see the word hit, right? Because if during the evaluation you see the word hit, the eval function will ask the environment, hey environment, what does hit mean? And it says, oh, hit is this function, right? And as you can see, just a little spoiler, hit, our Python implementation of hit, which you know from previously, that oh my god, I have to do that again. Define. No, I don't have to. I just need to do this. Right. It returns you the first element of a list. So I'm not. So here, if you're not familiar with the lambda syntax in Python, basically it just means function. Yeah. Okay. So hit is a function that takes something and returns you the first element. Sounds like hit, right? And tail is a Python function. Okay. Maybe I want to emphasize this. Tail is a Python function. Okay, that takes something, a list, and this is fancy syntax for saying cut off the first thing in front and return everything behind, right? So in case you are one of those guys, you know, who love syntax sugar, yeah. But what is interesting here is that all these things are Python functions. I have two comments. One is that this is cheating, right? In a sense that while doing our evaluation, we are just using Python to evaluate our stuff. But of course, we can see later that we can actually build on some primitives to build advanced stuff. Secondly, it shows that there's some. It's like a mapping from the Lisp symbol to the Python internal representation, right? Just like how in a syntax tree, like the word plus is, we define a little class called symbol, and for one we define a type alias called number, and so on, right? So we are like converting Lisp things into Python things. And of course this applies to all compilers as well, right? But here it's a lot simpler, because if you go back to the beginning, you can see it's quite a simple definition. Yeah.
So question.
Yes.
When it comes to these kind of higher level compilers,
Yep.
because like I said, I've never taken a
Mhm.
compilers class. Is it really just string parsing, trees,
Yes.
and then just function definitions? Or
Well, the
operator
the
definitions?
evaluation function is going to be, well, the lexer is going to be difficult to write, because imagine writing one for C++, the parsing as well. And for parsing, you will have problems like ambiguous parsing, because the language designer didn't know what he was doing. And some expressions can be parsed in different ways. And then you have the evaluation function, which kind of works the same way. You have an environment, and then yeah, it's pretty much the same, except that it has more stages, right? Optimization, type checking, and stuff like that, or some cunning memory allocation thing. So it has to allocate memory and stuff like that. Yeah, yeah.
Thank you.
But we're not covering that. It's just too much. Yeah. Okay. Good question. So I was saying that we're just converting Lisp stuff into Python objects and operations, but to the end user, which is me here, writing 1 + 1, to me it's like, oh, the Lisp thing is working, right? I have no idea how it works, but under the hood, it's just Python stuff, like adding and things, okay? And if you want, you could add something like, I don't know, download YouTube, right? And you can implement a Python function that downloads a file, right? It's severe cheating, but you could do that, all right? But we're not doing that. So let's see. So back to eval. Let's focus on evaluating this expression. Okay, how much time? I'm 1 hour in. Okay, that's good. So first, we evaluate this expression. So this expression is actually a list, right? It's a list, right? It looks like a list, walks like a list, smells like a list. It's a list. So is it a symbol? Nope. Is it string? Nope. Right? Is it not a list? Okay, I'll explain why later, right? But it's neither of the above, then it's otherwise a list. Great, it's a list. And then with the magic of Python syntax sugar, I like this a lot actually. I hate Python, but this is one of the nice things about Python, is that you can do this, right? And what this does is that it says, okay, OP is plus, stands for operator. And then your star args, or args, I'm actually not familiar with this, but I'll just go with args, is basically everything else, right? Which is your 1, and your star, your 2, and your 3, and blah, blah, right? Everything else, okay? In a way, it's like head and tail, but that's a coincidence, okay? So then we say, okay, now I've split the thing into an operator and the arguments. What do we do? Okay, is it an if? It's not an if, right? We're looking for a plus. Is it a define? It's not defined. Is it a lambda? It's not a lambda. We'll go into those later, yeah? But let's focus on this very simple expression. Otherwise, it is what we call a procedure call, which is a fancy way of saying call a function, right? Procedure equals a function, function equals procedure. These are just names that were from the Peter Novick implementation, but they're pretty much the same. So we can see it is a function call, and if you look at it, it makes sense, right? It's a function call to say, okay, I want to call the add function to add 1 and this guy over here, right? So let me just move that downwards so that we have enough space. We're talking about procedure calls here, right? So let's see. At this point, the operator is still a string, right? No, is it a symbol? Yeah, sorry, it's a symbol. It's a symbol. And the first thing we do is we say, okay, proc, which stands for procedure, is equals to the eval of op of n. Hopefully this rings a bell. Like, oh man, this is another recursive function, okay? So, inception time. So eval op, okay, so let's jump into eval op. In fact, let's jump into eval of symbol plus, right? So yeah, we're focusing on this. So if you go back up the function, is it a symbol? Yes, it is. It is, right? So let's find in the environment, okay? I'm not gonna go into the details of find. It is actually pretty, for weird reasons, it's complicated. I'll explain later. But in a way, it just looks up this global dictionary that we have, and it says, oh, you're looking for plus? Here you go. It's this Python function called op.add, okay? Then it says, okay, so proc equals to, abusing syntax again, Python function, Python add function, yeah? Okay. And then the values, so the choice of the word values is a bit weird here, but that's how Peter Novick did it. So, but this is basically means evaluate all the arguments. So we know that the arguments is this, and this is Python Lisp comprehension syntax sugar for basically saying for each thing in the list, evaluate the elements, right? So in short, what's going to happen is we're going to get vals equals to eval1 and eval star 2, 3. Did I get my thing right? Yeah. So this is what values is. So eval1 is trivial, but let's see how it works, okay? Because we are writing an interpreter after all. So is 1, okay, technically 1 is a number, right? So let's go through the cases. Is it a symbol? It isn't. Is it a string? It's not. Is it not a list? Yes. So it's a constant, right? So we just return it. So we just return. So eval number 1, no surprises. It's number 1. Yeah. And then we proceed to the next thing in the list, which is eval star 2, 3. Okay, and here we go again. Okay, yeah, recursion. Okay, let's go. So it's the same as the +1 case, except that at the end of the day, trust me, when you run the eval star, you get number 1 and 6. Yeah, I don't have time to go through the thing line by line, but you got to trust me on this. So let's assume that actually worked, and vals is a list of 2 numbers, 1 and 6, right? So what do we do? Now we have proc, we have vals. What do we do? Oh, we just call proc on vals. Basically in Python, it's add 1 and 6, which is 7, right? And then we return 7. That's it. So we evaluated this thing to give us 7. And this is how it really works. This is the squashing of the tree as we've seen in the slides. Okay, but here we're not just doing arithmetic. We're doing something a bit more fancy. So let's go through the other cases. So, but before that, anyone has any questions? Confused? Too much recursion? Yeah? Okay. So, let's see. Is it a symbol? Okay. First, it will check you will do some simple things, right? You say, okay, is it a symbol? Okay, yes, it is a symbol. And as we've seen just now, if it's a symbol, we try to look up in the environment, right? Like, this is our context, our cheat sheet. You say, oh, it's a plus, so I'm going to return you this function. Oh, it's equal, so I'm going to return you the equals function. Okay. Now, this is an exercise that you can do at home. Okay, maybe not, because it will be an actual exercise. There's a global environment. Okay, sorry, I'll go through that later. Just assume that this works first. is it a string? If it's a string, then return a string, right? Because you can't do anything further with strings, it's just strings. Is it not a list? We've covered this just now. If it's not a list, it must be like a number or some or some basic string or something else, right? So we just return that. Okay, and otherwise it's a list. And we jumped straight to the procedure call block earlier, but let's go through some more interesting things. Okay, if the op is a if, right? If it's a if, then let's do an example. What do I mean? Oh, come on. So if equals 1, okay, if 1 equals to 1, return 2, and otherwise return 3, yeah? Make sense? If 1 equals to 1, return 2, right? Then of course, if 1 is equals to 2, then return 3, yeah? Looks a bit stupid, but it will help in the explanation. So if the nice thing about Lisp, right, is that by looking at this, you can immediately write out the abstract syntax tree, like immediately. Just change parentheses to square brackets, add some quotes, add some commas, that's it, right? So if you could mentally imagine this to be the abstract syntax tree, I will go through the example. So first we know that op is if, right? Otherwise we wouldn't be talking about this. Args is, yeah, let's go with this example. Is this weird thing of equals 1, 2, and 2 and 3, right? Yeah? Any doubts? Did I make anything wrong? Okay. And then we do some Python syntax sugar deconstruction magic again to say, okay, the first thing is the test, the second thing is the consequence, the last thing is the alternative. This is Peter Novick terminology, but I guess it's obvious. So what it says here is that test is equals 1, 2, right? This is the test, right? If statements are like that, you do the test. If the test passes, yeah, do this. If not, evaluate the else block. Yeah. So, and the consequence sounds a bit serious. I know. And the alternative is 3. So then what's happening here is basically saying, first we evaluate the test, right? We evaluate the test. So eval test. I'm going to take a shortcut here. If you want to see how it works, you can go through line by line. But eval test is going to be true. Oh, sorry, it's going to be false, right? In case 1 is not equal to 2, right? So what this is Pythonic false, right? False in Python. This is not Lisp. We are in Python, the world of Python. And of course, if it's false, this is just if else. If it's false, then I just return the alternative, which is 3. That's it. And what this does is the expression is 3, and we want to return eval 3, and we know eval 3 is 3, right? There's nothing special about it. And of course here you may be wondering, why do I need to eval 3, right? Isn't it just 3? Well, if you were to do a more complicated function, let's say instead of 2, you want to return, let's say 1 plus 1, right? For some reason, your code looks like that, right? Okay, that wasn't a good example because I should have done 2 and maybe 1, 3, yeah. Because in this case, if we had been evaluating this expression, the alternative is not 3, it's going to be star 1, 3, right? And and then of course an expression is star 1, 3, and I cannot just return this immediately, right? It's going to be meaningless for the user, so we need to evaluate this as well, right? So for my toy examples here, there's some things where it seems trivial, like, oh, you're evaluating 3. Why bother to do that? But the reason why we evaluate is because sometimes we have complicated functions here. So We're just covering all our cases. Okay, so that's if. Wow, spent a long time on that. The next is define. So define is easy. So let's say define A1, right? And then A plus AA. Yeah. So A plus A is 2. So what define does is it basically says, okay, A equals to 1, right? But what does it actually mean in the interpreter? What it does, if you recall the environment, the global environment, the context, what it says is that, okay, hey environment, someone just defined A equals to 1. Can I upload that into the environment? And it says, okay, cool, right? So that in the future, when someone wants to call for A, right? So here, when I define A1, it adds A equals to 1 to the global context. And in the future, right, I can do a lot of things. And in the future, I call for A again. It will return me, it will look up the environment and says, okay, A equals to 1. Then, okay, cool. Then you just like retrieve it and do things. So here it does some fancy deconstruction again. Basically, define the expression. So OP is symbol. Sorry, OP is not symbol. OP is define. And the args is, in this case, is 1, right? So, no, sorry, args is A1, right? And then it does some fancy deconstruction. So symbol is A, expression is 1, and then it says, okay, please add this to the map. This is classic syntax of adding things to a dictionary, yeah? And then, once again, this looks trivial. Oh, why do I need to evaluate 1? That's because sometimes you want to add complicated stuff, right? Like B is 100, I don't know, plus 100, 2, right? Then plus BB, okay? So then in this case, we want to, before storing B in the environment, we want to flatten its value and then store it in the environment. So that's kind of how it works. The last thing here is this word called lambda, which if you have used Python, it's not unfamiliar. We've used it here. It's just a fancy way of saying inline function. Yeah, there's a long history why it's called lambda and not some other Greek letter, but let's not get into that. But what it does here is that it defines a function, right? So, let's see. Let's say I define, define plus, and plus is, plus is a lambda, which takes, let's make it simple, right? Add 1, right? This function takes a number and adds 1, okay? Very simple. It's a lambda that takes a function n. As you can see, we are entering parentheses hell, and then return. I hope I'm getting this. Oh, right. I always type n plus 1, so it should be this. And blah blah. Does it work? Okay. And then we do add 100. Okay, it works. Whew. So what this means is that I'm creating a function called add1. It takes a function. It takes a variable n and then it adds 1 to it. Literally, add 1. Yeah. So how it works is that op is lambda. We're just focusing on this guy here, right? We're focusing on the highlighted expression. So op is lambda, and what's the other one? Args is n. N and plus 1. Yeah, commas are too much, but okay, we're done. Okay, so these are the arguments, and then with the magic of deconstruction, params is n. Yeah, I hope you guys are seeing it, and the body is plus 1 n, right? And then it says, okay, create a procedure. Okay. Before I go into what procedure does, anyone has any questions? No? So let's go into the gory details of how it works. Okay, this is just the constructor, very easy, params, body, environment. Maybe let me just copy that. Params, body, function. Oh, yeah, whatever. Oh, environment. Yeah. So when you create a procedure, you want to pass in the environment as well because of evaluation and things. Yeah. So what happens is, where's my procedure? The constructor is boring. It's let's not go into that. The call function. So this underscore underscore call underscore underscore is implicitly called when you do something like this, right? So it's Python syntax sugar. That's not going to that, but just trust me that when you do this proc blah 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 bracket vals, internally it will try to find a call function in a class and you just do it. Yeah. So what it does is, okay, let's see, right? Call, because we're interested in call. Yeah. By the way, you can see that when we created our procedure, we did not evaluate the params and we did not evaluate the body, right? Because it's a function that we want to use for next time, so we shouldn't evaluate it now. There are no params and we cannot evaluate the body. We're just waiting for someone to retrieve the function and then evaluate it. So so here, if I were to use this add one, right? So if you go back to eval, it says, okay, what is add one? Environment. Is this a symbol? Yes. Can you find it for me? Yes. Then it would return this procedure thing, and then you call so params will be, okay, then when we call that, args is actually 100. Okay? So what it does is that you will say eval plus 1 n. Okay, once again, if you don't understand what I'm saying for the next 3 minutes, that's fine. Okay, so eval 1 n and create a new environment with params and the arguments and with the okay, global environment. Okay, I'm just gonna assume that, or some environment. Okay, so, and you'll be wondering what the hell is going on. Okay, so this is just another eval that we've seen so far, but we are evaluating plus 1n with a new environment with the following dictionary, and that is, right, if you look at the definition of environment, it says n equals to 100. Okay, take a while to digest this. Okay, and outer environment n, right? So let's look at these 3 lines. We're evaluating plus 1n, and by this time you guys should have a sense of how that's done, right? Just takes n plus 1. But then the eval function would hit n and it would say, oh, what is n? I have no idea what's n. Let me ask the global environment. And then it so happens that we are evaluating this in a new environment that has n as 100, right? Which is a parameter that we pass in. So it would say, oh, hey environment, what is n? And it would say, oh, n is 100. And then it would just take 100 plus 1, which is 101. Okay. And I did mention this thing called an outer environment, and you must be wondering, what is this outer environment? This is basically the so if I were to do okay, good. So we evaluate plus 1n, right? We know what n is, but do we know what plus is? What? Oh yeah, I know. So technically, we don't know what plus is because plus isn't in our environment, right? So instead, there's some mechanism here that says, okay, retrieve plus from the outer environment. So it's like another inception thing, you know, you have environments and environments, it's complicated, but it works, okay? So, that's it, okay? Like I said, yes?
Also, you can override the existing environment. If I just change plus and minus.
Yes, in the local environment, right?
Well, I'm local, could I just define plus as lambda n minus 1n, and then now plus now become minus?
That may be a bug. That could be a bug. Okay, okay.
Evaluated plus 1, 1 and 0.
Ah, okay.
Some languages do let you do that.
Yeah. Yeah.
Might be something.
Yes.
So what you're saying is you input a Lisp expression saying define plus space minus. Is that what you do?
I did define plus lambda n, then minus 1n. So
Okay.
therefore it just subtracts 1 from n. And
Yeah.
then, so now when you type plus 1, 1,
Mhm.
you get 0 instead of 2.
Good.
That's not good.
Well, some languages are designed like that. Yeah. So the reason why this is important is because if you run recursive functions, if you think about it, right, a recursive function, let's say it has a parameter n, right? But the thing is, there are many n's if you run at different levels of recursion. They cannot possibly refer to the same n. If that were the case, your thing won't work, which is why this entire environments thing is made. Yeah.
I'm curious, the question would be an original list. Would it allow this, or?
I don't know.
Okay, yeah, I'm curious enough.
I don't do Lisp
Okay,
as a
yeah, I
profession.
wasn't-
Yes.
Well, yeah, I hear two things. One is the concept of reserved words or keywords, and I
Mhm.
assume like to fix that bug, you just say, oh, if it's one of these, then you can't change it.
Yeah.
Second one is what I see and what you're just doing right now is lexical scoping. Is that the
Yes.
idea? Like each
It is.
each function call
Yep.
has a new set of
Correct.
variables.
Correct. And in fact, on that point, if you look at the find function in the environment, this is just, yeah, so it would try to find the variable in the innermost environment. So if it cannot succeed, it would just keep going up until it hits nothing, and it says, okay, I have no idea what's happening. Yeah.
This is scoping.
Lexical scoping.
If we are scoping, so that would mean the plus, I'm not overriding the plus from the original environment, I'm just creating a local, small environment.
I
how would
think so.
How can I then access the original, like the global environment?
You're not supposed to.
Uh,
Oh, no,
No, not access as an overriding, I mean, how can I step out of my local environment into the, like let's say
Or
accidentally
you want to call so you have two pluses and you want to call the outer plus?
Yeah.
Not supported.
You don't exit that scope.
Right?
The scope, so how do I exit the scope?
Well, you defined it in the global scope, so.
Oh, then I screwed up.
You can add a new feature to the interpreter,
Restart.
right?
Yeah, okay, sure.
Yeah. You can add a new feature, right? Some weird
No, I
feature.
get it. I was
Yeah, it's
expecting
possible.
it's not exhaustive. I get it.
Yeah, you can do it. You can actually implement it. Yeah. Yeah. Okay. So so time check. Wow, it's I have 17 more minutes, I think, right? And okay, let's see what we want to do. I know I spent a lot of time talking. So I did have a bunch of exercises, but maybe we'll just do a simple one, yeah? And then we move on to functional programming, which is kind of impossible to squeeze in 10 minutes anyway, but let's see. Okay, so if you run the exercise now, we have a problem, which there's a bug, right? Which is that it doesn't handle empty lists. And what I mean is that I can do stuff like, head of list of 1, of 2, or 3. I can do tail of list of 1 or 2. That's fine. But then if I want to tail, and does head work? I think head should work. Oh yeah, it collapses anyway. So this weird error is a Python error, right? It's basically the abstraction collapsing, the facade disappearing, and it's like, the guy who wrote this thing screwed up, right? He didn't support empty lists. So in fact, this is a limitation of the original Peter Norvig implementation. So I thought it's a good bug to fix. So the first exercise would be, how do we handle empty lists? So does anyone want to try? Yeah. So okay. While you think, yes.
But that would pose the question, what do we want to return though? 0, parentheses, some references.
So-
What's the symbol of the question?
Right, it's a good question. So, well, we want to define really an empty list in Lisp. No, yeah. So right now, if I do an empty list, right, I can't even define an empty list, and I should, right? I can define a single list, a singleton, but why can't I define an empty list? It doesn't make sense. Yes.
Is that an empty list? Isn't that just an expression?
There's an expression that when you convert to an abstract syntax tree, it's a list, right? It's a list in the end. So, list. So I can't do that, and I need an empty list to do all the fancy functional programming things that I want to do later. So let's see how it works, how conceptually we can fix that. So first, we know that X, right, our empty list, X, is going to be a list, right? This is the internal Python representation. Is it a symbol? No, right? It's not a symbol. Is it a string? No. Is it a constant? No. Otherwise, it's a list. And at this point, the whole thing collapses, right? Because we are deconstructing an empty list, which is why we get this value, this thing over here. Yes?
It's another if, I guess.
Yep.
Check the length of the list.
Exactly. You're right. So if we do this, and the answer is in main.py, I hope I can remember that. So if it's a list, and if the length of the list is 0, then we say, okay, you've got an empty list on your hands, we just return it, right? So let's try again, and voila, oh, it works, yeah. So, and we can take the, okay, you can't really take a head of a empty list, that will throw you an error, but you can take a tail, right? So, yeah, kind of, okay? So, we fix one bug. There are 2 other exercises. In the interest of time, I won't go through them. Yeah. Okay. So right now, okay, I know this workshop is supposed to be writing a Lisp interpreter, but all you did was open a file and watch me go through layers of recursion and stuff. But you can go through the exercises and even add new features like your outer scoping thing. It is possible, right? Yeah. And in the interest of time, so the other exercise was to fix a weird bug with the environment, which takes too long to describe. And the last exercise would be to fix the original function lex to support strings. So at this point, maybe I'll just open the actual function, the correct answer, to show you that it's not a one-liner, but we are still doing some considerable cheating. And I'll leave it to you to figure out how cheating it is. Yeah. Okay. Any questions so far? So we've written our first Lisp interpreter. Yay. Okay. Yeah. I wish I had more time. So now,
Question.
yes.
Would it be a good idea to do your lexing with regular expressions?
Generally, no.
Okay, why?
So theoretically, so going in theory.
Or can you repeat the question for the street?
Oh yeah. So Beach is asking, is it possible to use regular expressions to do the lexing? In some languages, yes. So it depends on the grammar of your language. If it's a simple language, you don't even need regular expressions. You can do the one-liner like we did. If it's a complex language, technically, it's a context-free grammar in the Chomsky hierarchy of languages, and you need to write a parser to parse the whole thing. But that is for those who are interested. Let's pull out the wiki, context-free grammar. This is what I said when I said parsing is interesting. There's an entire theory on this, and obviously I'm not going through that. But good question. Yes.
Can you, I think I missed the connection between regular expressions and this part. What exactly did regular regular expression? How did the regular expression move into
Right.
the next?
So in programming language theory, informal language theory, you have 4 different levels of expressiveness of languages. The most primitive is the regular expressions, and the next one, which programming languages are more suitable for, is the context-free languages. And of course, I know it doesn't make sense, right? What is context? Why is so free about it? Okay, I don't understand. You can read the you can read the compiler's book, and then the ultimate language is the recursively enumerable language, which some of you may know as a Turing complete language, right? Which is like, oh, you can do like almost anything, kind of. Yeah. So it is. So in a way, a context-free language is more expressive than a regular expression. So if you want to parse a context-free language, you cannot use a regular expression because it's too weak to parse it. Yeah. So there's a certain hierarchy on that.
So there's a really good post about on Stack Overflow about trying to parse HTML with regex, and regex can't do nesting, right?
Yeah.
And with this, what's a tree? A tree is a nested data structure.
Yep.
But the reason I wanted to ask that question is because when you look at this, you're like, why can't I just write a regular expression and do this? And if you start going that rabbit hole, you're going to have a bad time.
Yep. Yep.
So what I hear in that is in a context-free style thing,
Yep.
you're evaluating parts and replacing it with other things, and you're iterating until you reach some conclusion. Whereas in regular expressions, it's just one step. I'm just trying to compare the two ideas.
I'm not sure where to start. So, in a way, so a context-free language has a nested structure, and regular expressions don't. They are like, okay, state machines. They're technically state machines, but maybe that's too much.
If you want to
Yeah.
count the number of parentheses to know which parentheses to match
Yeah.
in regular expression, you can't. Regular expressions don't support that unless you know it in advance.
I see.
And that prevents the kind of nesting, because with nesting you have an arbitrary level of depth of nesting, and regular expressions don't support that kind of dynamic counting.
Yeah.
So you can't really write you can't write a program into your regular expression. Regular expression would just match something.
Right.
That's all it can do.
Right.
In a way, yes. Unless your program is so simple that, for some reason, your regular expression is sufficient to satisfy your needs. Yeah. So this is the grammar for Golang. The syntax here is BNF, Backus Now Form, something in programming language theory. So you can see it has a nested structure, right? Pretty weird. Okay, but you can see this is how they express things, right? Like, oh, an expression is a bunch of terms, a term is a bunch of factors, a factors is a bunch of stuff, and so on and so forth. Yeah, but this is not possible by a regular expression. Yeah, just saying. Okay. Okay, so here I'm cheating a bit. You can see how I cheated. I used another split. You can figure out how. Okay, with the limited time that I have, I will jump into functional programming and show you some things that can be done. Yeah. But I think we've covering the interpreter part was the main goal, so I think that's satisfied. The functional programming stuff is, I guess, is a bonus. Yeah. So now we have our interpreter. So just take 5-10 minutes ish. Yeah. So let's load the main one because the exercise one is full of bugs. So let's go through some exercises. So we can calculate the length of the list, for example, here. Of course, I didn't load examples, right? So, and I can calculate the factorial. So for those of you who don't know what a factorial is, 5 factorial is 5 times 4 times 3 times 2 times 1, which is 120, I believe. So factorial 5, you can write the Fibonacci sequence, the fifth Fibonacci number is 8. So I'll explain what it is later, and maybe I'll stop here. So as you can see, these functions were loaded from this examples file, and they were not in the environment, right? I didn't cheat by writing a Python function to do these for me. So I'm going to open the examples, and this is Lisp, kind of, right? That we are running in our interpreter to do stuff. And I think if there's one thing I need to bring across today, it would be probably the length function and the factorial function, just to show you that you can write things without a for loop or a while loop, right? So normally, in the world of Python or imperative programming, the normal way of writing the length of a list is something like, I don't know, right? So what is it? Int I is 0. No, you do something like, int length is 0. I know this is not Lisp, I'm just typing stuff in. And then you do like for int I is 0, and I don't know, right? I is less than something. I know it should be less than I, so it's weird. But let's say, right, you write a for loop or something, right? But clearly, in our interpreter, we didn't write any for loop, right? There was no for loop. So how is it? How is it possible that we managed to get the length of a list? So let's see what this length thing does. Okay, the convention here is if I have apple, I have apples. If I have x, I have x's. So when I say x's, it's like a list of things. So length is a function that takes a list of things and it checks a few things, right? First, is it an empty list? If it's an empty list, obviously the length is 0, right? There's nothing inside. And this is why we needed the empty list fix. Otherwise, this may be the mind twisting part. Otherwise, the length of a list is 1 plus the tail of its list. Okay? And so let's do that, all right? The length of an empty list is 0. The length of a list of 1 is 1, but that's really just 1 plus, I know I'm using syntax here, the length of the tail of list 1, which we know is an empty list, and that's 0, right? Which is 1. And the length of 1, 2, 3 is 3, but that's 1 plus the length of this, which is 2, plus which is 1 plus the length of this, which is 1. So 1 plus 1 plus 1 is 3. So it is, once again, a familiar sight, which is a recursive function. And the reason why this works is because we have the tail function, right? It somehow helps us deconstruct the list from its first element and everything else. And this is what allows us to iterate through the list. So that's length. And as you can see, we did things without loops, right? In fact, there is a loop. It's calling itself, right? So in a way, there's a loop, right? But it's not the usual loop that you see, right? For, while, and so on. The next one, which is the classic recursion example that you see in tutorials, is the factorial function. So in case you guys don't know, 0 factorial is 0. This is just math, right? Of course, I can't find that. 1 factorial is 1. 2 factorial is 2 times 1, right? And then 3 factorial is 3 times 2 times 1. But you can see, hey, isn't this just 3 multiplied by 2 factorial? Yes, right? And so 10 factorial is 10 multiplied by 9 factorial. I know, it's the problems. So basically, n factorial is n multiplied by n minus 1 factorial. So there's some recursion thing there. So we can do it here, factorial. So what factorial does is, it is a function that takes a single number n. If n is less or equals to 1, right, which is the what we call the base case, we return 1. If not, we return the product of n multiplied by the factorial of n minus 1, which is basically the Lisp way. So the on the left side is just a Lisp way of writing the thing on the right. Okay, and we can do a lot more weird things like the Fibonacci number, which if you guys don't know, the Fibonacci sequence is you start with 1 and 1, you add the two numbers, the last two numbers you get 2, and the last two numbers 1 and 2 you get 3, and 5, and 8, 13, and so on. Yeah, it's nothing. I mean, yeah, you shouldn't spend too much time on the Fibonacci numbers, but you can see there's some recursive structure here, because the nth Fibonacci number is basically the sum of the previous two Fibonacci numbers. If you can, I hope you are very conversant with Lisp syntax now that you can understand what this is. Yeah, so basically fib n, to use some Python syntax, fib n is equals to fib n minus 1 plus fib n minus 2, and unless you're a mathematician, they are quite useless. So, yes.
They're very useful for trading stocks. Those Fibonacci lines are useful.
Okay, we have a baller right here. Okay, a baller here in the room. Okay, cool. Okay, so, in fact, you can ignore me for the next 5 minutes. I'm going to talk a bit more crazy things in functional programming. But the thing you should know is recursion, right? You can do things without for and while loops. There are some useful tools. I'm going to introduce map. So let me load examples, load map. Oops, utils, right? So utils is, so I can do, okay, what is sequence of 5? It just returns me a list of stuff. You can see how it's defined in my examples. Everything from now on is pure Lisp, right? There's no cheating with Python. It's just building on the primitives of the things that we define in the interpreter, right? We have defined map as, okay, we have defined factorial as well. So what map does, and if you guys have used map in imperative languages, this shouldn't be a surprise. Just runs factorial on each of them, right? And there are other weird things like fold. So fold, I'll just run this function and see what you guys think about it. Yeah. So you can see it that it takes what we have evaluated earlier, right, which is this, and then there's this weird fold L thing, there's this plus thing, there's this 0, what the hell, right? Why am I adding fold L plus 0? And what is this number? So this number is basically the sum of the things in this. So we're taking the list and we are kind of like folding it into, we're squashing it into a value, right? So in essence, it means, okay, take this bunch of things, right, which we know is this list. Start with the value 0, and then just keep adding things to it, right, which is the plus here. We can replace it with times, right, and it will, okay, multiply with 0 doesn't work, okay, so I need to do 1. Okay, and yeah, I get a big number. You can trust me. Oh, okay, don't trust me, just trust the calculator. So you have weird things like, okay, I don't have time to explain, but the L here means folding from the left, and there's a R means folding from the right, and you may think, why? Why do we have that? Yeah, just because. And there are certain subtleties in why you want to fold from the left and from the right. But if you're using something simple like a plus, it doesn't really matter whether you go left or right. Yeah, or if you're doing stuff with lists, which I will show later. Yeah, you can look at the examples, the example list programs to see sometimes the left direction works and the right direction works. It is quite interesting. Part of my plan was to fix the string bug and then you can play with strings, right? And the reason why I wanted to introduce strings was that I wanted to take this one level further, and I wanted to write an interpreter in Lisp. Okay, so basically, yeah, it's a bit of an inception, but it can be done. So if you run this, right, it will actually, oh, of course, I didn't load my calculator, right? So you can do stuff like 4 times 2, and you get 8, right? So what we have done, or what I've done, you can see the example, is that I've used the Lisp language that I implemented or copied, and I wrote an interpreter in Lisp to calculate for this programming language, which is primary school arithmetic. It doesn't work perfectly. It doesn't deal with spaces, you know, because I was lazy to write. It's incredibly difficult to write a parser in Alexa in Lisp. It doesn't do stuff like 4 plus 1 plus 1 either. It only takes care of the first 2 operands. I cheated, I know. And to show you what it looks like, and to sort of bring this to an end, this whole thing is the interpreter written in Lisp with the help of other functions. But you can see at the end, calculate calc, right? And I think this is a very good way to end the session. There's no difference with other compilers, right? We take a string, we lex it, convert it to tokens, we parse it to create an abstract syntax tree, and then we evaluate it, and we get a function. Right? No different from the Python thing, but just a bit more hideous and difficult to write, a lot of parentheses, a lot of weird things. If you're interested, you could look it up. If you don't understand, you can ask me. There are a lot of limitations to this. Like I said, it works for 4 operators with 2 operands, with spaces in between, and nothing else, right? Yeah. So that's the end of the hands-on. I hope you guys had some hands-on. Hopefully, you can try it at home. And just want to end off with a few slides. So yeah, it was a bonus hands-on. So the interpreter is known as a calculator, right? And it is a sucky calculator, right? It's worse than what you have on your phone. So just want to answer a few, say a few thing. So for example, today, right, the Golang compiler is written in Go, right? So the question is, how did anyone even compile the thing in the first place, right? It's a chicken and egg problem. To compile the compiler, I need a Go compiler, right? So the thing is, so how it works is that the Go compiler, I'm just using Go as an example, but this applies to all programming languages, right? So the Go compiler was originally written in C to compile the Go code, which is what we've kind of done. We've written a Python, we've written our Lisp compiler in, Lisp compiler in Python. It is possible to write a Lisp compiler in Lisp. I just don't want to do it. It's just too tough, right? So a compiler that can compile itself, right, is what we call a self-hosting compiler, right? So as you can see, the theme for today is that there are many like loops and recursion and many meta things, which is kind of elegant if you think about it, but also quite confusing sometimes. And yeah, so the next thing is so the Go compiler is written in C, right? So they had to use a C compiler to do it. But the C compiler is also written in C. So how did anyone write the C compiler in the first place? The thing is, so some poor guy had to sit down and write the thing in the fundamental machine code language and bootstrap all the way from there. So we have to thank those guys from the past who did the hard work and did that, yeah. Which is why we have all these higher level abstractions today. So let's skip it. So, okay, we've covered all these. And just to reiterate, what we did at the end is that we are running a program in an arithmetic interpreter written in Lisp, which was running in a Lisp interpreter written in Python, which was running in a Python interpreter, which, by the way, the chances are that Python interpreter was written in C, right, C Python, and that C was compiled from C source code, right? So there's a lot of abstractions in between, but it's kind of invisible to us, but this is what happens. And like I said, you could potentially write a Lisp interpreter in Lisp or a Python interpreter in Python. The possibilities are endless. The concepts are the same. It's just how much pain you're willing to put up with. Yeah. Okay. Additional resources. There's the original Peter Novick thing. There's online ebook called Crafting Interpreters. It's a full textbook that's free online. It's on my list of things to do, and obviously I haven't gotten around to do it. I just used a simple Lisp thing, and 640 pages of beautiful typography and blah blah blah. Right. So they here, I think it's an exercise in building a language. Yes, dynamic typing, garbage collection, all the crazy stuff, right? Which our interpreter did not do. And that's it. Okay, thank you very much. You want to end off with some words?
So, I think everyone's been here before. Yeah, everyone's been here except you. So, welcome to the party. So we usually grab chicken afterwards. So if you guys want some food, we'll pay for it. Just come on, join us for chicken. And otherwise, thank you everyone for coming, and have a good evening.
Thank you.
And thank you, Darren.
Thank you. Thank you for listening to my very obscure, my topic on the very obscure things. Yeah, really appreciate
Pour
it.
one out to the COGs out there that wrote the original source code and allowed them.
I know, right? I know. Respect. So end stream?
Yes, please.
Yep, all right.
What's the title of the book again?
Crafting Interpreters? Yeah. Okay, that's it. All right.